Hi, welcome back to a new lecture from Transformers for Vision series. Today we'll be discussing about multi-head attention. I will give you a brief recap of our journey so far at the beginning, and then we will see how much we know, and you will truly realize that multi-head attention is in fact very simple because we have already discussed causal attention in the last lecture. So there are two approaches for implementing multi-head attention that we are discussing in this series. In the current lecture, we'll be discussing the approach using concatenating the context vector matrices that we get out of each attention head. And then after that, in the next lecture, we can discuss a bit more unified approach, which is adopted by modern large language models. If you don't know what is attention, self-attention, causal attention, etc., I highly recommend you to watch the lectures that are immediately before this one so that you will have better context. And especially if you have fairly good idea about the causal attention that we discussed in the last lecture, you will find today's lecture very easy. With that, let us get into the lecture. So first, let's have a brief recap of what all did we learn so far in this understanding of transformer architecture. We first looked at the transformer architecture itself as a whole. So here in the last part of this, I have a figure. So we looked at the transformer architecture as a whole, and then we discussed it in three parts: input, transformer block, and output. But there we did not go into details of the multi-head attention. So we kept multi-head attention alone separate, but we looked at the rest of the architecture. And then we started to discuss about attention. So first we started with Badhanov attention. In the context of neural machine translation. After this, we discussed about self-attention. And when we first implemented a simplified self-attention. So here we did not use any trainable weights. We simply said the attention score between two input embeddings or two vectors is simply the dot product between them. And once we have the attention scores corresponding to one query, we can normalize those attention scores to get attention weights. So this is what we did in simplified self-attention. But in the lecture following, we discussed self-attention with trainable weights. And here for the first time, we introduced the weight matrix for WQ for query, WK for key, and WV for value. And here we discussed that instead of directly taking the dot product between the two input embeddings, what we do is we transform those input embeddings into query key value spaces. Then we take the dot product of the transformed input embedding in query space and transformed input embedding in key space. So we got query.key transpose, q.k transpose. And then we said we will scale this by the square root of dimensionality of the key space, square root of dk. And then we said we will take softmax of this resulting attention weights. So what we get out of this is the attention weights. So we'll take softmax of this. And after taking softmax, actually before this it will be attention scores, and softmax will give us attention weights. And once we have attention weights matrix, we can multiply it with the value matrix. So this is basically the input embeddings converted into value matrix. So this was the final context vector matrix that we can get out of the attention with trainable weights. So this was what we discussed 2 lectures ago. And then after that, we discussed causal self-attention or masked self-attention. So this is what we discussed in the lecture before. So in causal self-attention or causal attention, what we discussed were the following. First, we have input embedding. So here we have 1, 2, 3, 4, 5. We have 5 input vectors in 3 dimensions. So total, this matrix will be a 5 by 3 dimensional matrix. And then we want to transform each of these vectors into the query space, key space, and value space. So query space dimensionality is 2 according to our assumption. So we said we will use query key value spaces of dimensionality 2 instead of 3. So to convert 5 vectors each of dimensions 3 into 5 vectors each of dimension 2, we used a transformation matrix of dimension 3 by 2. So 5 by 3 multiplied by 3 by 2 will be a 5 by 2 matrix. So this transformation matrix was the query weight matrix, which is a trainable matrix. Like this, we'll have another trainable matrix to convert the same input embeddings into keys and same input embeddings into values. So these three are the trainable matrices which perform the transformation of input into query, key, and values. Now, once we have these three, first what we do is we calculate the attention weights. So first, we try to get the attention scores. You take the dot product between query and key. So to get the dot product, you multiply Q with the transpose of key. So this is 5, 2 because you have 5 input embeddings, and in the query space, each of them is 2-dimensional. So it's 5, 2. The transpose of key is 2 by 5. And then the result of this matrix operation will be, matrix multiplication will be a 5 by 5 matrix. And this is the attention scores. And then we said to create masked attention, where we want to mask the future keys. Basically, query should not pay attention to keys that are supposed to come in the future. We want to mask the upper triangle. So all these values, we wanted to have it to be 0. For that, what should we do? We should have those numbers as negative infinity when we are applying softmax operation, because softmax operation is e raised to x divided by sigma e raised to x. So e raised to minus infinity is 0. So if we had minus infinity before we applied softmax, then those numbers will become 0 after application of softmax. So what we did was, the attention scores that we got, we converted the upper triangle into negative infinity numbers. Then we scaled the dot product. So this is the dot product, Q dot key transpose, Q dot or queries multiplied by key. And then we scale it. Basically, this scaling is done to reduce the variance or keep the variance of the resulting dot product numbers equal to 1. So we saw that the variance scales with square root of d. So if you divide by square root of d, where d is the dimensionality, in this case, the dimensionality is 2, the dimensionality of the query key value space. So since the variance of the resulting attention scores, which are these numbers inside this, is proportional to square root of d, if you divide the resulting matrix by square root of d, you can keep the variance close to 1. So this resulting thing is called scaled dot product, because we are scaling by 1 by square root of d. And the scaled dot product, we were normalizing using softmax. So softmax is applied row wise so that each row will sum up to 1. So this was the masked self-attention, because you are basically applying a mask. Negative infinity is the upper triangle. So this mask will produce a final output of zeros in the upper triangle. And then each of those rows should sum up to 1, because these are normalized attention weights. So the first item will simply be 1, because dream as a query has only one key to focus, which is dream itself. Dream cannot see big, because in this sentence, big comes after dream, and you are preventing the tokens or preventing queries from accessing the future keys. Big has access to only dream and big. So the sum of these two should be 1. Sum of these 3 should be 1. So every row should sum up to 1. Then at the end of the last lecture, we discussed about a dropout mask, which drops out these attention weights randomly at a certain probability. So if the probability is such that if we are dropping out at 0.5, let's say half of these items are masked, then we said the remaining numbers, the remaining numbers in this will be scaled by a factor of 1 by 1 minus p. So p is 0.5. So in this case, 1 by 1 minus p will be 1 by 1 minus 0.5 is equal to 2. The reason why this scaling is done is because when you are dropping out half of your items to produce your final output, you only have half items available on an average. So if you want to produce output of similar magnitude with just half the available weights, you have to scale those weights by a factor of 2 because half items are missing. So you scale the remaining ones by 2. So because of that, in the final output, actually this will be 2 instead of 1. This will be 2.0. This AND should be, so here the AND was the third item in the, or second item in AND was 0.2. So after application of mask, this 0.2 will become 0.4. Similarly, after application of mask, you have in the fourth row, second and fourth item gone, which means this and this is gone. So these two items will be scaled up by a factor of 2. Then here, second and fourth item is gone, which means this and this is gone. So remaining items are scaled up by 2. So this and this will be scaled up by 2. Then in the final row, this and this are gone according to the mask of the final row. So then remaining items will be scaled up by 2. So that is the final output that you get from a dropout mask. So this dropout mask was implemented to prevent overfitting. Now, in the result, we will not have these numbers. We will actually have numbers that are scaled up by 2. Okay, so now the goal of attention was the following, right? The reason why we introduced attention was because we wanted to have context vectors corresponding to every single input token. Because context vectors are much more information rich, input token just takes the semantic meaning. So if we have tokens for dog and cat, maybe they will point into a semantic space that correspond to animals. If we have apple and orange, those vectors will point to a semantic space corresponding to fruits. But if these words are already part of a sentence, then maybe the context in which these words are present are different. So maybe we should modify it a little bit to take care of the context. So this is why we were trying to create attention weights, so that using the attention weights, we can convert the input embeddings into context vectors. So we want one context vector per input token. Now with this much background information, let's see what is multi-head attention. So multi-head attention, as the name suggests, it has multiple attention heads that operate independently. So far in our discussion, we just had one query vector, one query matrix, trainable matrix WQ, one key matrix, and one value matrix. And these matrices were used to transform the input embeddings to query key and value. In multi-head attention, we will have separate WQ, WK, and WV corresponding to each attention head, and they will be stacked in parallel. So I have made a figure that explains the following. So I don't want you to focus on the right hand side yet. So I'm going to draw a rectangle so that this part is kind of masked. So just ignore this part. Just focus on the left hand side. You have your input embeddings. So this is one vector of 3 dimension. Like that, you will have, let's say, 6 vectors in the input. So those are 6 input tokens. Then instead of now having one query weight matrix, which creates one set of queries, here you have 2 query matrices. This is the first query matrix and this is the second query matrix, and these operate in parallel to produce 2 queries, 2 different sets of query matrices. Now, if I had 5 inputs, meaning I had 5 tokens and each with dimension 3, and if the dimensionality of my query key value space is 2, then this Q1 will be of dimension, what will it be? It should be 5 by 2. Q2 should also be 5 by 2 because each of them are processing the inputs separately, the dimensionality of the query space is 2, which means Q1 should have 5 input vectors converted into queries. Q2 should also have the same, and the dimensionality should be 2. So 5 by 2, 5 by 2. Same thing applies for keys. So there are 2 key matrices, which are learnable weights, which produces 2 keys, K1, K2. Similarly, there are 2 value matrices, weight matrices that are trainable, producing 2 value matrices as a result. So how is this Q1 produced? Q1 is simply X multiplied by WQ1. Q2 is simply X multiplied by WQ2. So basically input vector multiplied by the weight matrix. So weight matrix performs transformation of the input. Key is X multiplied by WK1. The second key is X multiplied by WK2, and similarly for value. So this part is simple. And now let's look at the right hand side part. So normally what would we do next? We would simply take the dot product between Q and K to produce attention scores. Then attention scores are scaled, then they are masked, and then they are normalized using softmax to produce the attention weights. And then after that, we apply dropout, right? These are the steps with respect to what happens to Q and K. And then once we have the final causal attention with dropout, you can multiply the result with values to get the context vector. So here also, it's exactly the same. Now I'm going to remove this, this white rectangle. So now we will have 2 matrices with attention scores. One corresponding to this query matrix, another corresponding to this query matrix. So this is now Q1 multiplied by, Q1 taken dot product with K1. So Q1 dot K1 transpose. And this is Q2 dot K2 transpose. So we are taking again the dot product between query and key, but such that Q1 is taken the dot product with K1, Q2 with K2, and whatever is the result of this dot product, it will be a matrix of what dimension? 5 by 5. I have drawn here as 3 by 3 just to save some space. But if our query space is having 5 tokens converted into 2-dimensional vectors, key will also be 5 tokens converted to 2-dimensional vectors. Like that, you have K1 and K2. So Q1 multiplied by K1 transpose will be 5 by 2 multiplied by 2 by 5 transpose, or 5 by 2 multiplied by 2 by 5. That will be 5 by 5. So the first set of attention scores will be corresponding to this will be 5 by 5 dimensionality. The second set of attention scores will be corresponding to the second attention head, second layer in the attention head. Again, that will be 5 by 5. And then what we do is we mask the attention scores such that the upper rectangle are all negative infinity. We also scale down with 1 by square root of d, which is 1 by square root of 2 in this case, because dimensionality of the query key space is 2. Then once we have the attention weights after we take softmax, so softmax of the masked scale attention scores. After we have the attention weights, we perform dropout so that randomly some weights are dropped out. Then we have, this is the final attention after applying the mask and after applying dropout. And then this we have to multiply with value, right? So we multiply the first, this one with value 1, V1. Let me just draw it. This is multiplied with V1, and the one below, which is the second layer of the output, is multiplied with V2. Now V1 will be 5 by 2. V2 will be 5 by 2. This will be 5 by 5. And this will also be 5 by 5. So when we multiply 5 by 5 and 5 by 2, the resulting one would be 5 by 2. So we will have now 2 context vector matrices. It's not context vector. So if I write it as context vector, it is wrong, but these are context vectors. So this S is important. Why? Because if I had 5 inputs, like this, if I had 5 input vectors, right? Then each context vector matrix will have 5 vectors like this. So 2-dimensional vectors, but there will be 5 of them. Like that, there will be 5 of them. And why is the dimensionality 2? Because we created this context vectors using query key and value whose dimensionality was 2. The input embedding dimensionality was 3, but the query key value space had a dimensionality of 2. And why do we have two context vector matrices? Because we had multi-head attention here with two attention heads. So one context vector matrix, the first one is created by the first attention head consisting of WK1 weight matrix, which produced K1 as the keys, WQ1 query matrix, which produced Q1 as queries, and similarly WV1 weight matrix producing V1 as values. Like that, you have two layers stacked parallelly, and these layers operate simultaneously but also separately. So you have two context vector matrices, and then what you do is you concatenate them to just produce one context vector matrix. So why do we call it as context vector matrix? Because you simply won't have just one vector like this, you will have 5 vectors. In our example, assuming we have 5 input tokens, we will have 5 context vectors. And what will be the final dimensionality of each of these context vectors? It will be 4, because you are concatenating two two-dimensional context vectors. Now let me draw this once to make everything clear. The dog, or something like this, let's say dream big and work for it. So how many tokens are there? There are total 6 tokens, and let's say each token is represented by a 3-dimensional vector. This will be a vector of dimension 6 by 3, a matrix of dimension 6 by 3. Then in multi-head attention, we have WQ1, WQ2, WK1, WK2, then WV1, WV2. Then this matrix passes through both of them to produce two queries, Q1 and Q2. The dimensionality of the query space is 2. So this will be 6 by 2. This will also be 6 by 2. If you want to produce 6 by 2 from 6 by 3, this should be 3 by 2. This should be 3 by 2. So this is WQ1. This is WQ2. This is Q1, Q2. Okay. Similarly, you will have keys and values. So there will be K1, K2 and K1. Both of them will be 6 by 2, 6 by 2. Then you will have V1 or V2 and V1, which will be again 6 by 2, 6 by 2. Now, query and key, we take the dot product. And after we take the dot product, we will have two 6 by 6 matrices. So this will be 6 by 6. This will be 6 by 6. Why do we have two layers? Because here we are saying we have two attention heads in the multi-head attention. Remember, in GPT-2, they had 12 attention heads. In GPT-2 small, in GPT-3, they had 96 attention heads. Okay. And then we perform scaling, softmax, masking, and finally dropout to get the final attention weights. And again, the dimensionality will be 6 by 6 and 6 by 6. Now we have to multiply this with the value matrix. So value matrix is 6 by 2. This is 6 by 6. So when you multiply 6 by 6 with 6 by 2, resultant will be 6 by 2. So we'll have two of them. 6 by 2 and 6 by 2. What is this? These are context vector matrices before we do the concatenation. And then we concatenate it. So here, each of them will be of 2 dimension, but like that, there will be 6 vectors, 3, 4, 5, 6, like that. Okay. And then we concatenate it in such a way that, so this part alone, maybe I can draw slightly better. That way I can show you the concatenation operation. So All right, so this is the first context vector matrix of dimension 6 by 2. I will give it a different color. And now this is the second one. This one can have another color. So you have two 6 by 2 matrices that are context vector matrices, correct? And then you concatenate them such that you are doing it row wise. So how does that look like? That will look like this. It will look like this. So first matrix should come first. So here I should probably bring this to the back layer to not confuse you. Yeah. So now if you concatenate, it will look like just one matrix of dimensionality, what? 6 by 4. So what happened is we had 6 input vectors of each 3 dimensions, and it got converted into 6 context vectors. So these are now context vectors of dimension 4, because each vector is now represented by 4 dimensions. So this is what happens in multi-head attention. So that is why, and where is the concatenation operation coming here? Here, the outputs you get from each heads of the multiple heads in the multi-head attention, you concatenate it. So now you can think of it like this. You can qualitatively say that each attention head is taking care of half of the dimensionality of final context vector. So final context vector has dimensionality 4. The first multi-head attention took care of the first 2 dimensions. Second head in the multi-head attention took care of the third and fourth dimension, the green ones. So you can think of it like that. But the actual reason why we have multiple attention heads is so that each attention head, because they have trainable parameters, it can train itself to learn different types of features in the input, so that the final context vector that comes out of this concatenation operation will be much more richer than if you had just one attention head with just 3 trainable weights like WQ, WK, and WV. So that is what is happening. So here, this one again shows the dimensionality. So if dream big and work for it is your input of 6 by 3, let's say you have multi-head attention of 2 heads. The first one will produce, the first output will be 2 context vector matrices, the each of dimension 6 by 2. Then they will be concatenated to produce one context vector matrix of dimension 6 by 4. Now, what if we had, instead of 2 heads, what if we had, let's say, 3 heads? And let's say the dimensionality of each of the query key value space was 2. Then this output will be 6 by 2 only. This is not going to change. But instead of 2 context vector matrices, we'll have 3 context vector matrices. And each of them will be concatenated. So 6 by 2 will become what? Will it become 6 by 4? No, it will become 6 by 6. Because now you have 3 things to concatenate. And what about if my dimensionality of the query key value space was 3? So let's say Q, K, V dimensionality was 3. Number of attention heads equal to 4. And input dimensionality equal to, let's say, 4. And number of tokens equal to 6. What will be the final context matrix looking like, context vector matrix looking like, the final one after concatenation? So tokens, you have 6 tokens, input dimensionality is 4. So you have a 6 by 4 matrix. Now the query key value space individually, they have 3 dimensions. So this 6 by 4 will be converted to 6 by 3 for query, 6 by 3 for key, 6 by 3 for value. Now these are 6 tokens in 3-dimensional space. Using this, the attention weights that will be produced will be 6 by 6. And then this attention weights, after applying the mask and after applying dropout, will be multiplied with the value matrix. So 6 by 3 and 6 by 6 will be multiplied such that the resulting dimensionality will be 6 by 3. Now, this is the resulting dimensionality of the context vector matrix from one attention head. Like that, how many attention heads do you have? You have 4 attention heads, which means when you concatenate, your final dimensionality will be here. In each attention head, the dimensionality of each vector is 3. You have 6 vectors, each vector has a dimensionality of 3. But like that, you have 4 attention heads. So if you concatenate, finally, you are concatenating along the row. This will become 6 by 12. So this is how it works. So these were random numbers I just picked. This is not how actual GPT numbers look like, but just to show you how to calculate, right? So this is what we finally have. Okay, so now in GPT-2, we had 12 transformer blocks in series. So this is the transformer block diagram, and this diagram we had looked at in the lecture where we tracked the journey of a token. So this transformer block is just one picture, but like this, there were 12 of them in series. And within each transformer block, GPT-2 had 12 attention heads in parallel. So the multi-head attention had 12 heads. But that is within one transformer block. Like that, there are 12 transformer blocks in series. And in GPT-3, they had 96 transformer blocks in series. And inside each transformer block, they had 96 attention heads in parallel. But that's within one transformer block. Like that, there are 96 transformer blocks themselves. So this is how the multi-head attention works. Now what we can do is we can try to implement this in Python code in the simplified fashion. And in the next lecture, we will see how do we apply the multi-head attention in a much more matrix multiplication friendly way. So these are the vectors that we are considering at the input. Dream big and work for it in 3 dimensions. Each of the row will be one vector. So you have 3 columns because you have. And this nn dot linear basically defines the matrix multiplication using which we transform our input. It also allows us to add the bias if we need. So we thus define W query, key, and value. Then we have dropout. So nn dot dropout function helps us easily define the dropout mask. And this tri U is the upper triangular matrix, which makes sure that we are applying the mask such that upper triangle items are initially negative infinity, and then we apply softmax. Then in one forward pass, what we are doing is we are calculating key. Key is W key of X. So what here is happening is into this nn dot linear function, we are passing X. X is the input. And that inputs get transformed using a matrix whose dimensionality will be dn multiplied by d out. So dn is dn will be 3, d out will be 2. So 3 by 2, as we saw earlier. Same thing happens to produce queries and to produce values. Now here, B is a new dimension that we are introducing, which is batch size. Usually we will have batch as a parameter, but other than that, number of tokens is 6. Here batch dimension is 1, batch size is 1. Number of tokens is 6 because we have 6 words. D in is 3. Then attention score is nothing but the dot product between queries and keys. So queries multiplied by transpose of keys. So can you guess why we do transpose of 1, 2? The reason is we are the first dimension or 0th index dimension is the batch. So the dimensions that we want to exchange is the dimension where number of tokens and the input dimensions are coming, which is the first and second dimension. 0th dimension is the batch. So since 0th dimension is the batch, that we don't involve in transpose. We transpose this dimension and this dimension, which is dimension number 1 and dimension number 2. So queries multiplied by the transpose of keys. So this at is the Python symbol for matrix multiplication. Then attention scores, we convert to attention weights. So first we have mask. In that mask, we are defining torch dot minus of torch dot infinity, which are minus infinity values. And these minus infinity will be there introduced in places where we have upper triangle. Then attention weight is nothing but softmax of the scaled masked attention scores. So this is now the masked attention score. Upper triangle will be negative infinity divided by keys dot shape of -1 raised to 0.5. So keys dot shape of -1 is the last dimension of the keys matrix. So keys matrix dimension was 3 by 2. The last dimension is the number of columns, which is 2. So -1 means we will pick the shape of the last dimension. So keys dot shape of -1 will basically be equal to 2. And 2 raised to 0.5, which is square root of 2. So we are taking square root of 2. And then softmax is applied along dimension equal to -1, which is softmax is applied such that the columns will be preserved along the rows the softmax will be applied. Then attention weights, final attention weights will be these attention weights plus dropout applied on top of it. So after dropout is applied at a certain probability, you will have masked certain weights being masked, and remaining weights will be scaled up by a factor of 1 by 1 minus p, where p is the probability with which you are masking. And then final context vector is nothing but your attention weights multiplied by values matrix. So attention weights in this case will be, you have how many tokens? 6 tokens. So attention weight should be 6 by 6. Values will be 6 by 2 because you have 6 tokens and 2 as the dimensionality. And then you will have the final context vector. So this is how we perform the calculation. Now let's run this just to make sure that we have all the class defined. And then dimension at the input is inputs dot shape of -1. Again, this will pick the number of columns in the input. Number of columns in the inputs is 3. Number of rows is 6 because we have 6 tokens, each tokens of 3 dimension. So din will turn out to be 3. We can just print din. So din should be 3 and d out is 2. So that's what we are printing. And then we define batch. So batch is such that torch.stack of inputs comma inputs dimensionality equal to 0. So here you can see that you have inputs stacked 2 times to produce a batch size of 2, but they are the same inputs. Ideally, we will have different inputs, but here we have stacked the inputs 2 times to produce a batch whose size is 2. If we had this repeating 3 times, we will have a batch size of 3. See, first dimension is batch, second dimension is number of tokens in each batch, third dimension is the dimensionality of the each token. Okay. So here we can actually go with one batch also, no problem. So if we just have inputs comma, then it's just one batch. So one batch, 6 tokens, 3 as the dimensionality. Now what we do is we define this class. This is the new class that we are defining called multi-head attention wrapper. Basically, this is a wrapper which is around the previous causal attention class that we have defined. So into the causal attention, we are passing input dimension, output dimension, context length. Context length is what? 6. Dropout, we will say false. So I will show you where this is being passed. So first we say MHA, multi-head attention equal to, it's an object, which is an instance of this multi-head attention wrapper class, into which we are passing D in, D out, context length, 0 for dropout. So nothing is being dropped out. Number of attention heads equal to 6. Okay. And then that is being passed in over here. Query key value bias is false. And then these passed values are also passed into the causal attention class. And one thing you might notice here is this for loop is because we are processing these attention heads. Although in reality it happens in parallel, we are defining a for loop so that attention head number 1 processes its input first. Attention head number 2 processes its inputs next. And then those outputs you get from attention head number 1 and number 2, you finally concatenate. So here we are doing it in series, but this is not a very efficient way to do it. You will see that in the next lecture. But you can concatenate the outputs that you get from both of these attention heads. So here you say this is the concatenation operation. So final thing that you get as a return is for each attention head, the output you will be concatenating. So you are calling head of X, and the output is whatever is returned is this guy, context vector. So like that, you will be two context vector matrices because you have two attention heads. So let's just run this and run this. So here we just want to print the final context vector. So final context vector is this 6 by 4 because you have concatenated the context vectors from both attention heads. So this is now the final context vector. And I also want to show you what if my batch size was 2. If my batch size was 2, so now it's batch size 2. Same inputs we are repeating. Ideally, it will be different. And you will have two such context vectors corresponding to each batch. The numbers are the same, but you see, this is the first set of context vectors. Okay, let's look at the dimensionality. First of all, batch size is 2. So this is the first batch. And this is the second batch. Second batch of what? Second batch of context vectors. How many context vectors in each batch? 6 context vectors in each batch. What is the dimensionality of each context vector? 4 is the dimensionality of each context vector. What was the dimensionality of the input vector? 2 was the dimensionality of input vector. How many input vectors were there in each batch? There were 6 input vectors in each batch. So input dimensionality counting batch size was 2, 6, 2 over here. Sorry, 2, 6, 3. Yeah, input dimensionality was 3. And then, so that was 2, 6, 3. And here context vector dimensionality is 4. Why is it 4? Because you have two heads in the multi-head attention. What if we had, let's say, 4 heads? What would have been my final output? If we had 4 heads, each head is outputting a dimension of 2. Like that, you have 4 heads. So your final dimensionality for each context vector would have been 8. So let's try that. So number of heads equal to 4. Then you see 8. Why? 1, 2, 3, 4, 5, 6, 7, 8. So each context vector is of dimensionality 8. So this is the first batch. This is the second batch. You have 6 vectors in each batch. Each row of this one batch is one vector. So this is one vector. This is second vector, third context vector, like that. And each context vector has a dimensionality of 8 because you have 4 attention heads. Each attention head is producing a context vector of dimension 2. Then when you concatenate them, you get a dimensionality of 8. So this is how multi-head attention works. In the next lecture, we will see in detail how multi-head attention is actually implemented in practice, because this for loop is not good because now you are implementing each attention head in series, while in reality it has to happen in parallel. Only then LLMs can utilize GPU processing to improve the speed of training. Right here, what if we had 40 attention heads? The code will significantly slow down for sure because of the for loop. I mean, this is still fine, but if I had, let's say, 400 attention heads, I don't want to print the context vector. I just want to print the shape. So now it's taking a little bit, it took a few more seconds. If this was 4,000, it will take more time. See, it's taking few more seconds. And as this dimensionality increases, I mean, number of heads is anyway not 4,000 in any model. It's only 96, but then you have many of them to process in series. But in general, you will notice the effect of things slowing down because you are running a for loop. The best way to know track this is you simply keep a timer before and after execution, and this timer will tell you how much time it took for you to run. In the next lecture, we will see how can we do this without using this for loop, just by using simple matrix multiplication. So I hope you understand the idea of multi-head attention. In multi-head attention, you have multiple attention heads happening, processing the input independently. Then finally, you have outputs, which are multiple context vector matrices. Then those matrices concatenate along the row to produce context vectors of that concatenated dimension. So if you had 2 attention heads, and if each attention head is producing context vector of dimension 2, your final dimension of each context vector will be 4. So, and why do we have multiple attention heads? Why not one attention head? Because if we have multiple attention heads, each attention head is now having 3 trainable weights. And these trainable weights are so valuable because it can learn patterns in the data, and each attention head will take care of different aspects of the relationships between the tokens in the data. It's very hard to exactly say what is the role of each attention head, but the fact that you have different attention heads trying to learn patterns from your data, it makes the learning process much more efficient and the final context vector after combination much more richer. So I hope you enjoyed this lecture. Please try implementing this yourself. It's very easy to implement. If at any point you have any doubts or confusion, pause the lecture, watch the video again, and do take very good notes. Also code along with this, or after you finish the lecture, at least you try to define the code and write this yourself. The detailed mathematical implementation and code implementation of multi-head attention we will see in the next lecture. So take care. See you soon. Bye.